What do you need to know about acid-base chemistry? You ought to be able to know right now how to rationalize differences in acidity based on electronegativity and inductive effects, based on hybridization, based on size and polarizability, based on resonance, aromaticity, and so on. But one nuance that is probably ignored in undergrad organic chemistry is the influence of solvent on acidity. So we're going to start by talking about the most famousest of solvents, and that is water. We've just learned about the hydrophobic effect in water, but we need to talk about acidity in water and something called the leveling effect. And the leveling effect is related to the idea that an acid stronger than the conjugate acid, and this is true for any solvent, but especially for water, an acid stronger than the conjugate acid of the solvent can't be present in any appreciable amount in that solvent. So I'll give you an example of that. And maybe this is obvious, but for example, HCl and water are in equilibrium with H3O plus and Cl minus. The pKa of HCl is -9. The pKa of H3O plus is around -2. You know how to do equilibria. The strongest acid loses its proton. What that means is the equilibrium constant here favors products by like 10 to the 7. Okay, so that means that in water, there is no HCl. Which may sound weird because, of course, you can buy concentrated HCl in water, but what it really is hydronium and chloride. Does that make sense? So when you're in a solvent, part of the leveling effect, particularly of water, is that there's no acids in water that are stronger than -2 in terms of pKa. Because if they were, they're just going to protonate water. And so then the question arises, how do we know the pKa's of acids that are stronger than water, or stronger than H3O plus? And there's a story there that we could delve into, but it involves measuring pKa's in different solvents. A similar principle is that a base that is stronger than the conjugate base of the solvent also can't be present in any appreciable amount. And to illustrate this, again, we'll use water. Let's use tert butoxide as a base and water as an acid. And then, of course, tert butanol was the conjugate acid of tert butoxide, and then OH minus. Again, find the acids on either side of the equation. The pKa of water is around 12. The pKa, oh, not 12, sorry. What was I thinking? 16. Turns out the pK of tert butanol is around 19. So again, products are favored by a large amount. 10 to the 3 at least. So in water, you're going to, if you use tert-butanol, you're mostly going to have hydroxide, which again is fine, and this is actually why you don't use water as a solvent for tert-butoxide. It's kind of a waste of money. You can buy NaOH, I think, more cheaply than you can buy tert-butoxide. So again, the principle is that if the solvent can gain a proton or lose a proton, then the pKa of the solvent's conjugate acid or the pKa of the solvent itself influences the acidity of what's present. And you can't have anything more acidic than in water than H3O plus. You can't have anything more basic in water than OH minus. And so that also means that you can't measure the pKa of, for example, tert-butanol in water. So let's talk about the influence of solvents other than water. And first, notice what happens usually when, for example, an acid loses its proton, right? You end up with charged species, right? And so you might expect acidity to depend on the ability of the solvent to stabilize charges. And so that's why we talked about non-covalent interactions in chapter 3, because it's important to understand those types of interactions as ways in which the solvent can stabilize charged species. So if we think about pKa's in organic solvent, let's give some examples of organic solvents, right? You've got the totally nonpolar ones like 2, 4, 6 hexanes. Then you have slightly more polar ones, for example, ethanol or methanol. Methanol is a protic solvent. So which one of these two is better at stabilizing charges? Okay, good. Is that like a read your scriptures and say your prayers question in Sunday school? Everybody knows the answer, so nobody wants to say it. Okay, good. And why?
Hydrogen bonding.
Okay, you got hydrogen bonding, and then you got dipole interactions. Yep, good. And methanol is not just a polar solvent. It's also something we're going to call protic because it has a proton that it can lose depending on the pKa of what's in solution. And then, so methanol can be both a hydrogen bond donor and a hydrogen bond acceptor. Okay. There are a number of solvents that we could put here that are polar and protic. There's other solvents that we could add that are polar but non-protic. So one of these would be DMF, dimethylformamide. This is polar, but it's non-protic. Okay, meaning there's no acidic proton there, right? So this could be a hydrogen bond acceptor, but not a hydrogen bond donor. It would be good at solvating cations, right? Because you've got this polar electronegative oxygen, which should have a partial negative charge on it, but it shouldn't be very good at solvating anions. Similarly, you've got DMSO, which you can draw in a couple of ways. Dimethyl sulfoxide you can draw like this, or if you want to, you can draw it like this. It's got a hypervalent sulfur. It is like DMF, polar, but non-protic, and like DMF, can be an H bond acceptor, and it's good at solvating cations. Okay, and there are some others that we could talk about, but this may be decent enough to get started with. Okay, yeah.
Methanol you're talking about, or ethanol?
What's that?
Is this methanol you're talking about?
Oh, I'm sorry, ethanol, but you could also put methanol on this list too. It's similar properties. Let's see, and there are other solvents you could consider. I think one more that your text talks about is acetonitrile, which is just this. Again, this has the ability to be a hydrogen bond acceptor, but not a hydrogen bond donor, and it can be good at solvating cations, but not anions. Incidentally, we're going to learn later about SN2 reactions. You know, the solvents that you choose need to be solvents that can solvate ions, especially cations, because you want to strip the cation away from the nucleophile so that the nucleophile can do the attacking. Okay, so some principles about non-aqueous solvents in general you're going to find. pKa's first. pKa's are generally higher in organic solvents than in water, because the organic solvents are not as good at solvating ions. They are worse than water at solvating ions. Second, for the same reason that organic solvents are generally poorer than water at solvating ions, differences in acidity tend to be spread out over a wider range of pKa's than in water. And then finally, the last thing we need to consider is, as we're thinking about other solvents and measuring pKa's in them, we have to beware the ion pair. If the solvent that you're using, what is an ion pair? This would be, say, Cl- and H3O+ as an example. Or an ion pair could be NaCl. The ion pair is close contact between charges. And what this means is an incompletely dissociated ion pair. If you're in an organic solvent, the acidity that you measure, if you're in a nonpolar solvent, the acidity that you measure might be the acidity of the ion pair. Let me give you a better example. Ammonium chloride. Right? If you're in organic solvent that doesn't solvate ions very well, that means the ammonium and the chloride are going to be very close to each other, and therefore the measured acidity in organic solvent might be the acidity of the ion pair rather than the cationic acid. So you have to be just a little bit careful in interpreting the data. Yes?
What about sodium acetate?
Sodium acetate, yes, though in its form, in this ion pair form, it already lacks the acidic proton. Right, the acid that you'd be interested in, I guess, is acetic acid.
Mhm.
Once it's sodium acetate, it doesn't have that acidic proton anymore. So I'm not sure what pKa you would measure unless you're thinking about the alpha protons. Yeah. All right, so let me illustrate this with some data. I'll just show you some pKa's to give you, pKa's for various acids to give you a sense of the impact of solvent. These aren't numbers to memorize, but rather trends to be able to rationalize. So I'm going to write solvents. We're going to have water, methanol, DMSO, DMF, and acetonitrile, which we'll abbreviate this way. And we'll just compare a few acids here. Here is acetic acid. So by thinking about the pKa, again, we're measuring the ability of acetic acid to give, to lose its proton to either of these, any of these solvents. In water, the pKa of acetic acid is 4.8. In methanol, it's higher. Okay, why is that? Well, presumably because methanol is not as good at solvating charges as is water. DMSO, it's even higher. Why is that? Well, DMSO can't hydrogen bond like methanol can, and it's about the same in DMF as it is in DMSO. So we're sort of seeing here poorer ability to solvate charges leads to higher pKa's. All right. Here's another paranitrophenol. Has a pKa in water of about 7.
You know
In-
about the one for the
Yeah, the values in acetonitrile are not measured for all of these acids. This is just a table from the book. So, yeah, sorry.
well, it should be higher than water.
You would expect it to be about higher than water, about the same as these other polar aprotic solvents. Yeah. All right. So in methanol for paranitrophenol, it's a little bit higher, around 11. But going from polar protic to polar aprotic, there's not as big of a change. And we'll see this as a general trend, though it is quite a bit higher in acetonitrile. Where a conjugate base can be stabilized by resonance, the solvent doesn't matter quite as much. And I'll show you another example of that. And then lastly, here is anilinium, the conjugate base or conjugate acid of aniline. In water, pKa of around 5, and there's only a couple numbers here. In DMSO, a pKa of 3.2. In DMF, a pKa of 4.2. So interestingly, the trend for cationic acids is reverse of the trend for neutral acids, right? It's all about solvating ions. These neutral acids, when they lose a proton, become negatively charged. In contrast, this cationic acid is charged, and upon losing its proton, it becomes neutral, right? So it should be easier to go neutral in organic solvent. And that's why these pKa's in DMSO and DMF are a little bit lower than they are in water. All right, questions so far? All right, let's look at a few other, yeah, go ahead.
So the effect, it's not from this compound. It's from its ability to lose the proton.
That's right, the pKa is
Yeah.
for this reaction, HA or HB plus, reacting with the solvent to get A minus and HS plus, or B and HS plus. Oops. So, for example, the reaction in water would give you hydronium as the conjugate acid of the solvent, or the reaction in methanol would give you protonated methanol as the conjugate acid, or if it were DMSO, would give you protonated DMSO as the conjugate acid of the solvent.
The ability for this solvent to solvate this acid, for the third one, it's not the strength of the solvent, it's the ability of the acid to lose its proton.
Well, in all cases, you're mixing. Well, the problem is that you can't measure those two things independently, right? The ability of the acid to lose its proton is also affected by the ability of the solvent to pick up the proton. In other words, we need to lose the idea from general chemistry that an acid dissociates to give us H plus and A minus. That happens in the gas phase, but nowhere else. And so in any solvent, when we're measuring acidity, we need to consider not only the acid losing its proton, but then also the solvent. And let's suppose it was, again, DMSO. Yeah. Here's one of the resonance structures of DMSO. You have to consider there's two things going on here. First, the acid is losing its proton to become the conjugate base. But where is that proton going? Well, it's being picked up by the solvent. And this is why solvent influences here's the acids on either side of the equation. And the pKa that you measure is, or the equilibrium constant you measure here, is going to be affected by not only the acid losing its proton to give this species, but also DMSO gaining that proton. And that's why the pKa's are different in different solvents. Yeah?
So, do people just find the pKa's for each individual solvent that they can put their acid in, or do they, like, for one acid, they say, oh, this is a representative acid, and so what we're going to do is we're going to find the change in pKa for each solvent, and then we can just find all the other acids in this one solvent.
Yeah, that is a good question, and your text, I think, explains it a little bit, but not in ways that I was able to understand very well. But essentially, to compare the pKa's that you've been taught for acids are all ranked relative to water. But the way you do that is you take an acid that you can measure the pKa effectively both in water and in an organic solvent, right? And then once you've got that number, you can rank pKa's relative to that with acids that are even more acidic. And so it's sort of this staggered laddering approach where you have certain things to compare to. You have some things that can be accurately measured in both solvents, and then relative to that, then you can back calculate out the pKa of this acid that's stronger in this solvent. You can now back calculate how strong it would be in water. It's, I think, more complicated than that, but that, yeah. By far the most common solvent other than water that you can find pKa's for is DMSO. And just for fun, I'll show you a place, oh, this was gecko feet. Let's see, I'll show you a place on the internet. It used to be maintained by Professor Hans Reich at University of Wisconsin-Madison until he died tragically in a bicycle accident a couple years ago, and then the ACS, or I can't remember who took over maintenance of the pKa table. Oops, sorry. But it's an incredible table that you can go to and find pKa's of just about anything that's known, along with references. So let me, of course I can't, pKa tables, Hans Reich. Professor Reich was at Wisconsin when I was there, taught the NMR class, was really amazing. So here you can get pKa values from various sources in DMSO, and you know, this is a multi-page document where you can think of any acid you might be interested in, and the pKa's are known, and there's references there. So if you ever find yourself needing to sort of estimate acidity to determine whether a solvent is good for a certain application or not, coming to this resource is a good place, and it's organicchemistrydata.org. But if you Google pKa table DMSO, it'll bring you here. All right, other.
What do you say about acetone as a solvent among those ones you listed?
What would I say about acetone among those solvents?
What would you say about it?
I don't know what the pKa's are in acetone, though I would predict they would be similar to these, because acetone, again, is a polar but aprotic solvent. Okay. Other questions? Okay, so let me show you a couple more examples of the impact of solvent. Again, here is the acid. We're going to list pKa, again, comparing in water and DMSO. HBr in water, at least compared relative to water, has a pKa of -9. In contrast, in DMSO, it's a lot less acidic, okay? And that's related to, again, the fact that, well, hold on, let's keep showing you the trend. HCl has a pKa in water of -8. In DMSO, it's 1.8. HF has a pKa of 3.2 in water. In DMSO, it's 15. Okay, so the principle here is that the poorer solvation of ions makes the intrinsic stability of the conjugate base even more important. CB is for conjugate base. Recall, I'll draw the conjugate base here. What did you learn in undergrad? Why is Br minus so much more stable than F minus?
Come again?
So you learned in, when you learned about pKa's, say, of these three acids, that HBr is more acidic than HF, and that's related to the fact that Br minus, the conjugate base, is more stable than F minus. Bromide more stable than fluoride. Yeah, go ahead.
Because of the size of the bromine?
Yep, size and
Sure.
and polarizability, right? Bromine is larger, spreads out electron density over a larger amount of space. It's way less electronegative than fluoride, but when comparing conjugate acids, if there's a size difference, the size difference matters. For comparing conjugate base stabilities, the size difference matters more than the electronegativity difference. So notice that the difference between HBr and HCl is a little bit, well, actually, let's see, relative, that's 1 pKa unit, that's basically 1 pKa unit there. 2 to 15, that's what, 13? Anyway, it's spread out a little bit more in DMSO relative to water. So one of the things you're also going to see is that in general, pKa's are higher in DMSO for reasons that we've talked about. All right, I'm trying to think of some other examples to illustrate this. I said before that if the conjugate base is highly conjugated, if it's stabilized by resonance, then solvent differences don't matter as much. For example, trinitrophenol has a pKa of 0.4 in water and a pKa of 0 in DMSO. And presumably this is because if the charge on the conjugate base is spread out via resonance, it's already quite stable and maybe doesn't need a lot of help from solvation. Another example of this is the following sort of beta dinitrile. These protons that are alpha to 2 electron withdrawing groups, and therefore the conjugate base is resonance stabilized. The pKa's are identical in DMSO and water. So another principle, pKa's are generally higher in DMSO. In poor solvating solvent, intrinsic acidity differences matter more, and so pKa's are more spread out. And then if the conjugate base is highly conjugated, or in other words, resonance stabilized, solvent matters less. All right. Want to show you just a couple more comparisons. Phenol versus methanol. pKa of phenol in water is 10, of methanol is around 16. In DMSO, 18 versus 29. So notice that the pKa difference here is basically 5 pKa units. Here, it's 11 pKa units. So that tells you, that illustrates that in organic solvent, the pKa's can be more spread out. And finally, there's one observation that's just interesting. pK of water is around 15.6 as measured relative to itself, but in DMSO, it's 32, which is a huge difference, even bigger than the difference between methanol in water and DMSO. So the question is, why is water so much less acidic in DMSO than methanol? They both have the same pKa in water. And the idea is that in water, OH minus is highly solvated. In fact, instead of OH minus, it's really OH minus with several water molecules along, where N is like around 8. So instead, through hydrogen bonding, you have a network of water molecules that surround OH minus and consequently delocalize that negative charge. So that's not possible in DMSO. I'm going to just draw a few more to get the idea across. That kind of thing isn't possible in DMSO because DMSO is not a good hydrogen bond donor. So you're really comparing this highly delocalized conjugate base versus the highly localized conjugate base of OH minus in methanol. And that reflects the fact that in methanol, that methanol is not as good of a hydrogen bond donor as is water. It's just got fewer protons and it's less polar. And that's sort of what I told you before. When you think about water as a solvent, think about H3O plus or OH minus. It's more complicated than that because after a while, it's difficult to tell who's the OH minus and who are the water molecules. It's just like you've got a group of water molecules that's one proton shy or one proton down. Yeah. Okay. So this kind of thing shows up in biology all the time, and the reason is that protein interior environments have are different polarity than exterior environments. So we talked about protein folding last time, about how upon folding, let's see, yeah, non-polar groups are sequestered in the protein interior, whereas polar groups are on the protein exterior. This is because of the hydrophobic effect, but that means the interior of the protein is relatively non-polar. And just as we would predict, when you change to a less polar solvent, the pKa's can be different. So that's similarly true in various enzymes. So I want to show you a couple examples of this. No, really not. Well, I guess I don't have it. Let me see if I can find it. I want to show you the images of the crystal structures of these proteins rather than just telling you about them. So I have to find the original place where I have this. Dizzy yet? I'm dizzy. Here we go. All right, so these are three enzymes: lysozyme, acetoacetate decarboxylase, and a protease called papain or something like that, not sure. And their active sites contain residues that are important for their biological activity. Glutamate 35, this is a carboxylic acid. Lysine 115 in acetoacetate decarboxylase, this is an ammonium ion. And then histidine in papain, or however you say it, I should figure that out, is an imidazolium side chain. And so we're comparing pKa's in water. For a carboxylic acid like glutamate, you're looking at around 4.2. In the nonpolar enzyme interior, it's 6.5. And that can be important because in enzyme interiors, you're going to need functional groups to remove protons, and you can't remove protons as a base if the pKa of your conjugate acid isn't just right. So the interior environment can change the pKa of various acidic groups to facilitate chemistry. So here is lysozyme, here is glutamate F35, you're seeing a stick and, well, let's see, a ribbon diagram of the protein with side chains shown as sticks. Carbons are either gray or orange. Red is oxygens, blue is nitrogens. Superimposed on this is a space filling model, so you can see that this glutamate is sort of not exposed to water. It's sort of surrounded by a bunch of other things, and that influences its pKa. Here is a crystal structure of acetoacetate decarboxylase. Here is the relevant lysine. It's currently involved in what looks like an imine bond with acetoacetate is this ketone, this beta ketone. This looks like it's actually an inhibitor rather than the actual molecule, but the mechanism involves forming an imine with this carbonyl oxygen. And that's what you're seeing here. But notice if lysine needs to form an imine with that carbonyl, it needs to be a nucleophile, right? And in its ammonium state, that's not a good nucleophile. It's got to lose its proton. Well, in the protein interior, it is suddenly much easier to lose its proton. In fact, at pH 7, that lysine shouldn't be protonated anymore. And you can see again, it's in the interior of the protein where the nonpolar environment can change the pKa. And then lastly, here's just the histidine in papain, and in this case, histidine needs to act as a nucleophile, needs to act as a base. So you want to stabilize histidinium, and in organic solvent, it's much, or rather in a nonpolar environment in the enzyme active site, it's much more favorable for histidine to exist in its non-protonated form, imidazole form, and so it becomes a much better base in the interior of the protein. All right. So these are things to think about and just be aware of. Questions you want to ask? Okay. Well, I think there's more we could talk about. There's some things about gas phase acidities, proton affinity. I don't think we're going to care about that very much. So, yeah, that'll be it on chapter 5, and next time we'll move on to stereochemistry. Again, that'll be pretty brief, 1, maybe 2 lectures, and then we'll start getting into reactions and kinetics. All right, have a good Monday.